Hello, my name is Youngtak and I'm going to present about my research with the title Developing the Smart Farming Index Across Countries. Below is my contact info, including my school information, which is Cranbrook Schools at Michigan, USA, and below is my email. So for an introduction, I'll give some background information about smart farming and its effectiveness. So smart farming will help farmers to precisely select the input and improve their knowledge of factors that affect agriculture by one, managing planting, two, measuring productivity effects and management measures, number three, tracing and controlling farm produce security, and number four, monitoring plant growth. The effectiveness of smart farming will be divergent among all nations due to mainly three reasons. Number one, agriculture differs a lot depending on the site of farming, as most of the impactful resources and factors are related to the environment. Two, there could be limitations to apply smart farming in regions where internet infrastructure is not sufficient. And three, regions that are dependent on agriculture and are willing to invest more in the industry will more effectively adapt to the change. So for a conceptual framework, we selected data sets from the World Bank and online websites to create the index that shows the potential effectiveness of smart farming in each nation. So we categorized the data sets into three main categories, and the first category is the agriculture environment, and the data sets included in this category are plant species threatened, land for cereal production per capita, water productivity, and emissions per capita. Plant species threatened shows the numbers of endangered species, and this value demonstrates if the nation is an environment where plants can thrive in. And for the economic status, we included GDP per capita, agricultural output per capita, and agricultural employment. For the last category, which is resources and infrastructure available, the data sets I use are internet users, secure internet servers, R&D spending, energy use per capita, renewable resources per capita, and human capital. And the created index will be useful for nations to determine how actively they should adopt to this new concept of smart farming. So now is the data and methods section of creating the index. So we mainly use the PCA method. So following the standard PCA procedure, the tails of all variables are reduced by 1% up and down to eliminate all the influence of extreme values or outliers. And all variables exhibit significant standard deviations indicating that they can be subject to PCA. And in order to be as comprehensive as possible, our index includes the 13 variables that were mentioned before in the conceptual framework, and we apply PCA to the variables following the standard methodology of Baxter and Joliffe. So on the right is the data chart for each variable. So there are the mean, median, standard deviation, minimum, maximum, and number of countries for each of the variables. So here are the steps. So after first comparing all intervariable correlations, we check the normality of all variables and transform any that require it. And normalization and trimming outliers to 1% from the data is required because PCA is not scale invariant. Then we adjust all variables to the same scale and index them within a range of 0 to 100. And to do this, we calculate the ratio of the difference between the actual value of variable and its minimum value to the difference between maximum and the minimum value and multiply this ratio by 100. We then run the PCA using all 13 transform variables, and the PCA produces the same number of components as the number of variables used in the analysis, which is 13 in this study. These components are basically linear combinations of the variables. And last, number of components chosen for the final index should be such that the associated ion value does not go beyond 1. For all statistical analyses, we use STATA version 17. So here's the table that represents the ion values and proportions of explained variance in the dataset for each component, and the table notes present various test results for PCA. The value of Kaiser-Meyer-Oken index, which compares the correlations between the variables and partial correlations, resulted in 0.84, where a value for the KMO test above 0.8 is considered to be good and adequate, thereby indicating the efficiency of the PCA and adequate sampling. Bartlett's test sphericity is also satisfactory, rejecting the null hypothesis that the observed correlation matrix does not deviate significantly from the identity matrix. The scale variability is also acceptable with a Cronbach's alpha value of 0.77. The principal components ion vectors are presented in full in table A1 in the appendix. The analysis indicates using 6 components since component 6 has an ion value below 1. With 5 components, the analysis can account for about 81% of the variance in the overall data. So here's the formula that we use for the PCA index. And below, there's a chart for unweighted average. So the coefficient of each principal component is equal to the proportion of variation explained individually by each principal component divided by the total cumulative proportion of variation in the whole data explained by all 6 principal components. As an alternative to the PCA-based index measure, we also create an alternative index using the unweighted arithmetic average of all 13 transfer variables and finally transforming it into a 0 to 100 range. Since the correlation between the two indices is 0.81, we only continue with the PCA-based index in the subsequent analysis. So here's some analysis for the created index. So here's the global heat map of the index, and which shows which nations has the high values and which has the low values. And the top 5 nations that are ranked high in the index are Iceland, New Zealand, Australia, Norway, and Finland. The next is histogram and the associated normal distribution of the smart farming index, and it shows the density of the group frequency. So the density of the index in the range of 0 to 20 is very high, and the density decreases as the value of the index increases. And next is the potential improvements of the overall index, which shows the impact of each variable in the change in the value. So the top improvements in the terms of policy are increasing human capital, R&D spending, internet users, water productivity, and secure internet servers. So this is our conclusion. So the data collected and used for the construction of my index represented the nation's agricultural environment, economic status, and resources and infrastructure available. With those data sets, we use the PCA to weigh each data set differently based on their relation and contribution to the application of smart farming. The top 5 nations rated by this index are Iceland, New Zealand, Australia, Norway, and Finland. So nations can use this index for objectification of problems existing to adopt smart farming and can potentially improve their environment for a more effective application. Some suggestions include case studies about smart farming applications specific to a single or limited number of nations, or the exploration of the socioeconomic effects which a successful adaptation of smart farming can bring. And with the index constructed and the general evaluation provided in this paper, further research is in this broad emerging field of smart farming is also possible. So here's the appendix, which shows the benchmark and the alternative index for each of the nations. And here's the references used in the research. Thank you so much.